So the first law of thermodynamics, often referred to as there is no free lunch. My kids used to go to a public school where there was free lunch, right? Are those lunches free? No, somebody's paying for them, right? They're just free to the kids that go to the school, right? Somebody's paying for those. There is no free lunch, okay? So thermodynamics is the study of energy and its interconversions. The first law of thermodynamics, stated a little more scientifically, not referring to food, the total amount of energy in the universe is constant. So you cannot generate or produce new energy. You can only convert energy from one form to another form. So you can't get something for nothing. Any questions about that? People used to try to invent these perpetual motion machines that would just keep going without any source of energy. They were all frauds, or there was a source of energy that was not recognized at the time. But you can't create energy. It's just not possible. So conservation of energy means that the total changes of energy summed up has to be zero. So something gains energy, something loses energy. Just like a financial transaction, one person loses money, the other person gains money. So again, we can look at this energy gauge idea over here. Here, the energy gauge of the system is at half full. The surroundings are a quarter full. There's some sort of a transfer of energy. The system is now less and the surroundings are more. So the system lost energy, the surroundings gained energy, just like a financial transaction. If you add those two things together, they add up to zero. So it's like if you have a checking and a savings account and you transfer money from your checking account to your savings account. Did you gain money? No. Did you lose money? No. You can't gain money by moving money back and forth between your two accounts, right? You can't gain energy, create energy by moving energy back and forth. So we can express it this way. Delta, and that triangle is a Greek letter delta. We use that to mean change in. And almost always it means the final minus the initial. So if we think about a change in temperature, if the final temperature is 100 degrees and the initial temperature was 50 degrees, it's a positive change, meaning the temperature went up, right? So delta energy of the universe, the change in energy for the universe equals zero. That's always going to be true. And we can express that as the change in energy of the system plus the change in energy of the surroundings. One of these is positive, the other is negative. And when they add together, they add up to zero. Of course, there's more kinds of energy. It couldn't just be that simple. So internal energy. This is what the E refers to. Internal energy is the sum of the kinetic and potential energies of all the particles in that system. So that's the energy of the system. The thing about that is, how do you measure the energy of a system? The problem is you really can't measure the energy of a system. All we can do is measure the change in energy. So if we look at the change in energy, change in internal energy, that is going to depend on how much energy the system had to start with and how much energy it has at the end. It's just the difference between them. That's called a state function. And we talked about that back in chapter 1, I think it was. The state function is something that only depends on the starting point and the ending point. It doesn't depend on how you got there. So a change in altitude is a state function. Doesn't matter if I get to the top of the building by taking a helicopter or climbing up the side of the wall like Spider-Man, the change in elevation from the ground to the roof is the same. Now, the distance I traveled might be different, right? The distance traveled is not a state function. The state function just depends on where you started and where you end up. So, the change in internal energy is equal to the final energy minus the initial energy. So we can use this with chemical reactions and say that the change in energy for the reaction is equal to the energy of the products minus the energy of the reactants. Oh, yeah. I guess we didn't talk about state functions before. It's here. I don't remember anything. I just look at the next slide. Okay, state function. Okay. Reboot. Okay, so change in elevation. Climbing the mountain instead of the building. I went off track. I went off script and did something else. So let's think about getting to the top of this mountain. It's 10,000 feet. You could take path A, which has you winding back and forth, and you're going to travel 12 miles to get to the top of the mountain. Or you can take path B, which goes just straight up the side, involves a lot of climbing, and that path is only 5 miles long. So the distance traveled depends on whether you take path B or path A. Your change in elevation is the same regardless of how you got there. There's another way you could get there, a helicopter, right? You could catch a helicopter here and you'd fly up and a bit above, and then you come back down and sit there waiting for the guys climbing up the side like idiots, right? Your change in elevation would be the same as the guys that climb the mountain, right? The distance traveled is different though. So the state function only depends on where you start and where you end, not on how you get there. Any questions about that? The state function only depends on where you started and where you end up. And the beauty of state functions is that we can calculate them in different ways. So we don't have to know how you got to the top of the mountain. All we need to know is the elevation here and the elevation there, and we can say what your change in elevation is. We use energy diagrams to try to help us picture what's going on. Because energy isn't something we can see. And I don't know about you, but I'm a very visual person. I need to be able to see stuff. And if I can't actually see it physically, I need to have a picture of it in my brain so that I can pretend that I'm seeing it. So energy diagrams are something we use to try to help us out in that respect. So here, looking at this reaction of carbon dioxide decomposing into carbon and oxygen. So this is an energy diagram. And so we always use up as being positive and down as being negative. And so if you go up, you're increasing in internal energy. So our reactants are down here with a low amount of internal energy. And the products are up here with a higher amount of internal energy. So what happened is going from reactants to products, the amount of internal energy increased in this system. Now that doesn't mean the energy of the universe increased. This energy had to come from somewhere. This would be like looking at the balance in your savings account, and it went from this amount to this amount. It increased. That money had to come from somewhere, right? We'll deal with that later. But the change in energy here is larger than zero. It's positive because the final is larger than the initial. So this we have the system is getting energy from the surroundings. That's where the energy comes from. There's the system and the surroundings, like your checking and savings account, and it's just between. So the system here is gaining energy. Energy is coming in. The change in energy for the system is positive. That means that the change in energy for the surroundings has to be negative or less than zero. Any questions? Yes.
Can you correlate products and reactants with system and surroundings?
The products and reactants are both part of the system. Yeah, and the surroundings is everything around it. Good question. Any other questions? If we take that reaction and run it the other way and have the carbon and the oxygen combine together to form CO2, well, carbon and oxygen have the same amount of internal energy they had in the previous example, and carbon dioxide has the same amount of energy it had in the previous example, right? That's its internal energy. Here, the reactants were at a higher energy, and the products were at a lower energy. So when we take this number and subtract that number, we get a negative change in energy. So that means that this system lost energy. The energy went out. It's like when you pay for something, the money goes out of your wallet. You feel positive or negative about that? Negative. Somebody gives you money coming into your wallet, that's positive, right? So that's the sign convention for energy. Energy is like money, coming in is positive, going out is negative. So here we have the change in energy for the system is negative. Energy is flowing from the system to the surroundings. The change in energy for the surroundings is positive. Any questions about that? And the balances moo at us. So when energy flows out of a system, it must all flow into the surroundings. And these are sort of nebulous definitions, system and surroundings. So system is the part of the universe that we're interested in, and we can define that any way we want. Surroundings is everything else. We don't always have to consider the whole universe. Sometimes we can just consider the area around the system. But energy, if it flows out of the system, it has to go into the surroundings, and it all goes there. So energy flowing out of a system, the change in energy for the system is negative. Energy flowing into the surroundings, then the change in energy for the surroundings is positive. So the change in energy for both of these things is the same. One's positive, one's negative. It's like transferring money between your checking and savings account. There's a word missing there. Right? If I take $10 out of my checking account and put it into my savings account, and I look at the balances, on the online banking, because we don't keep check registers anymore, right? So the checking account has a negative 10, but the savings account has a positive 10. All the money that moved went from one to the other. That make sense? That's what the energy's doing. Okay, so how is energy exchanged? There are two ways that energy can be exchanged. Through heat or through work. Heat and work are not state functions. They do depend on the process. So those would be like the distance traveled in going from the bottom to the top of that mountain. The change in elevation is the same regardless of how you get there. But the distance traveled is different. The distance traveled is like the heat and the work, not state functions. They do depend on the process. So heat and work are the ways that energy can be exchanged. So we can say that the change in energy is equal to the heat plus the work, because those are the methods or the means by which energy is transferred. So we have sign conventions for these things. So heat is positive if the system is gaining thermal energy, negative if the system is losing thermal energy. So that goes along with the energy being money, and you put yourself in place of the system, and if energy is coming in, it's positive. If energy is going out, it's negative, just like money in your wallet, right? And then there's work. So work being done on the system versus work being done by the system. Anybody here just really enjoy doing manual labor, going out and working in the yard, digging ditches? Okay, one exception. So this isn't going to work for you. The rest of you, that would probably be a negative experience, right? Go dig this ditch. Get all these rocks out of this field, right? You are doing the work that's negative to you. Work being done on the system. Well, what's that? Well, maybe think of a massage. Okay, someone's coming up and massaging your shoulders and it just feels so good. They are working on you, right? And that's a positive experience for you. For them, they are doing the work, and so that would be a negative experience because it's going out. Does that make sense? We have to be able to keep these sign conventions straight. So the change in energy, the change in internal energy, is positive if energy is flowing into the system. That could be heat, thermal energy, or it could be work being done on the system, or you could think of as for the system. The change in internal energy is negative if energy is leaving the system. That could be through thermal energy going out or work being done. So let's look at some of this. Here we have a pool table. And this pool table is a good one. It's got a nice smooth surface. So here we have, again, the white ball and the purple ball. So this white cue ball has an initial kinetic energy of 5 joules. This is energy of motion. So this ball is moving. As the ball moves, because this is a real table, right, that ball's going to slow down, isn't it? It's going to slow down because of friction with the table. So it's losing some of its kinetic energy as it rolls across the table. That energy is not being destroyed. It is heat energy lost to the table. Friction results in heat. So if you take your hands and you rub them together really fast, you feel warmth, right? That's from friction. If you've ever drilled a hole in a piece of wood and foolishly touched the drill bit right afterwards, it's really hot because of friction, okay? So kinetic energy can be lost from the system into the surroundings as heat energy. So it's slowed down a little bit when it gets here. It's got 4.5 kilojoules of kinetic energy left when it gets over here and impacts the purple ball. So this is a thermal energy, a heat transfer. When the ball hits and the purple ball goes speeding off, the remaining kinetic energy has been transferred to the purple ball, and now this white ball has 0 kinetic energy. So it lost 4.5 joules in doing work on the purple ball, and it lost 0.5 joules heat from the friction as it rolled across the table. So its total loss is negative 5 joules. It started with 5 joules, it's ending up with 0. So those 5 joules of energy, 4.5 went into work done on the ball, other ball, and 0.5 into friction lost as it rolled across the table. Does that make sense? Here we have similar situation, but now this isn't a very good pool table. It's got a very rough surface. So now as this ball rolls across the table, because the surface is rough, it's not going to roll as well, right? Try to roll a tennis ball on the grass versus on a sidewalk, right? It's going to roll really well on the sidewalk, and it's not going to roll very well in the grass because there's a lot of friction, a lot of resistance. So here we give this ball the same amount of kinetic energy to start with, but now because of the rough surface, it's going to lose 3 kilojoules of heat as it moves across. So over here, it only has 2 joules of energy left to do work on the purple ball. The total amount of energy is the same. The change in energy is a state function. It does not depend on how it got from this condition to that condition. It only depends on the initial and final conditions. But work and heat are not state functions. So the work done and the heat lost do depend on the process. Make sense? So change in energy for that white ball were the same in both instances, smooth and rough table, but heat and work were not the same. So delta E depends on the velocity of the white ball before and after. If we look at Q plus W, it's the same in both instances, even though the values of Q and W are different. So the energy lost by the first ball is equal to negative, because this energy is going into the surroundings. So the system and the surroundings, and we can put that negative sign on either side. It just means that those numbers are equal in magnitude and opposite in sign. So heat we refer to as Q. It's a transfer of thermal energy. And this occurs when things have a difference in temperature. Temperature, what's that? Temperature is a measure of the amount of thermal energy. You can think of it as a measure of the average kinetic energy of the particles. So heat flows from things with high temperature to things with low temperatures. And we experience this all the time, right? If you pack your lunch and you heated up your burrito and you had a frozen Go-Gurt and you stick them in the same container, 3 hours later, what's the temperature of those things? Is the burrito still hot and the Go-Gurt still frozen? No. What temperature will they be? The same as each other eventually, right? Because the heat from the hot burrito will get transferred into the cold Go-Gurt. And they will keep transferring energy until the temperature of both is the same. That's called thermal equilibrium. No net transfer of heat occurring. So heat always flows from high temperature to low temperature. Okay, let's look at an example here. A cylinder and piston assembly. So we're defining the cylinder and piston as the system. Is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during that expansion, what's the value of delta E? So this is an exercise in learning what these little terms mean. So the equation is that the change in internal energy is equal to Q plus W. It's the heat transfer and the work either done by the system or done on the system. So here we're saying that the system absorbs 559 joules of heat. So Q is equal to 559 joules, and we have to decide, is that positive or negative? It's positive because we are the system. We're thinking about, is energy coming in or going out? Energy is coming into the system. It's like energy going into, money going into my wallet. I'm going to put a positive sign here just to emphasize that we're thinking about the signs. And then it says it does 488 joules of work. So W equals 488 joules. And then we have to decide, is that positive or negative? It's negative because the system is doing work. Okay, we're doing work on something that's a negative. Having work done on you is a positive. So we've identified what Q and W are. The change in internal energy for the system is just the sum of these two things. So we've got 559 joules plus W. And W is a negative number. Now, sometimes students get a little weird when they see negative signs. have to go back and talk to your elementary teacher, get out a number line or something. This is the same as 559 joules minus 488 joules. Or you can do 559 plus negative 488. If you need some help with this, let me know. I won't laugh at you. It's a serious thing. So 71 joules. That's a positive number. So the cylinder and piston assembly overall has gained energy in this process, even though it did some work on the surroundings. Any questions?